Hello, everyone. It's my great pleasure to welcome all of you to today's online seminar on interval methods in control engineering. And it's my very great pleasure to welcome today Nedialkov, who is full professor at the McMaster University in Hamilton, Ontario, Canada. And he's an expert on solving differential equations, ODEs, and also differential algebraic equations, partially also not only with respect to the development of novel numerical methods, but partially also with respect to handling uncertainty with the help of interval arithmetic. And concerning interval arithmetic, he was also one of the important persons during the standardization process that led to the IEEE 1788 standard for interval arithmetic. And now we're looking forward to your presentation, Ned, on sub-ODEs, that simplify Taylor series algorithms for ordinary differential equations. Ned, the floor is yours.
Thank you. Thank you for the nice introduction. This work with John Price, we've been working quite intensively in the last, I don't know, year or 2 months. So I'll start with an introduction and I'll explain how sub-ODEs work and why we look at them from a differential algebraic equation viewpoint. Then we have a MATLAB solver called ODTS, and I will talk about its performance. I'll talk about some history and some conclusion. There's a paper we submitted 2 months ago to the Science Journal for Scientific Computing. So, about our problem. So we're concerned with Taylor series a solution of an initial variable problem for an ODE system. And this is in general and dimensional system. Now, in these Taylor methods, we assume that the function defining the ODE is built using basic arithmetic operations and standard functions such as exponential, sine, and so on. And typically non-differentiable functions like absolute value, min, max, and conditional structures like if statements are excluded because we need to compute Taylor coefficients, and we need this thing to be sufficiently differentiable. Okay. Very briefly about Taylor series methods. So if we take a Taylor series method for this problem, these are one-step methods. So in each step, we compute Taylor series to some order of the solution. So we have to compute the coefficients of the series. And then we sum up with a suitable step size and we move to the next point. Okay, so on each step, Taylor series, sum up and move to the next point. And we have usually step size control. Now, if we take Runge-Katoa multi-step method, the function f is like a black box. We give input, we get output. But here, we need the function to be available as code because we need to execute the function and compute coefficients in terms of recurrences. So we need the representation of f. And we need recurrences for the basic arithmetic operations, like plus, minus, and so on, and for the standard functions, like exponential, sine, and so on. Now, most Taylor method implementations, if not all of them, use individual recurrences for each standard function. And what's nice and important about this work is that we eliminate this need for separate recurrences. And this talk is also about how we do this. Okay. What are advantages of Taylor methods? Well, they can work at any order. The work per step is like big O of p squared. And this may look expensive. It is, but also we can take large steps as we have larger order. And in double precision, typically orders anywhere between 15 and 20 is typically the most efficient choice to integrate. Now, Taylor methods they're good for very accurate computations, especially using arbitrary precision arithmetic. For example, Roberto Berrio in 2005, he was doing long-time modeling of solar system motion, and order 180 was typical. Another thing is there is work by Rob Corliss and Sylvain Ille showing that the complexity is polynomial in the digits of precisions obtained, and typical methods cannot achieve this. Okay, so if you take a Runge-Kutta multi-step method to get very high accuracy, one has to take very small steps. Okay? And what's really been useful in the validated area for validated solutions of ODEs using interval arithmetic, the truncation error of the method can be really easily enclosed by computing these Taylor coefficients with intervals. And this is one of the main reasons why Taylor series methods have been popular in the interval area. Okay. How to compute coefficients? Now, if we do this symbolically, it doesn't work very well in general because the expressions can blow up in size. And we do automatic or algorithmic differentiation. And here's a simple example to illustrate this. So if we take this simple problem, and if we write this, the series for x in this form, then differentiating, we get this thing. And if we square, multiply x by x, this thing here, we get these expressions for the coefficients. And then we have to evaluate one by one, and we do this recursively. So x1 is the initial condition squared. Once we get x1, then x2, by equating this term, we get the second coefficient. And then by equating the third term, we get the third coefficient and so on. Okay? So in this case, we compute this by propagating numbers, not symbolic expressions. And it's not difficult to see that to get k coefficients, or let's say p coefficients, one need to do p squared work because of these multiplications. Okay? And there are recurrences for the arithmetic operations and for the standard functions. Okay, so this is about AD. Now, in this talk, I'll use the notion of a code list, and I'll explain what we mean by a code list of an ODE. So if we have a size n ODE, we define the code list as a sequence of assignments of this form, and I'll explain what this means. So we have input values, which are the values from x1 to xn and t, and then we compute intermediate variables, xn plus 1 to xn, and xn plus 1 is an alias for t. Okay? Now, this phi j, this either basic arithmetic operation, it's either a basic arithmetic operation or standard function. So essentially, this gets broken down in binary and unary operations, and these fj's are phi j's of this sort. This notation means that this is the vector of xi's that xj is a function of. Or simply speaking, we use values that are already computed. We don't use a variable that doesn't have a value yet. And then from these intermediate variables, certain variables, output variables that contain that are part of the output vector. So we have a set of indices such that certain part of these variables, they give the output vector. All right? And this is very much what happens when we evaluate an ODE function. Essentially, internally, it goes through unary and binary operations. Okay. And what is this whole sub-ODE idea? Suppose we have in ODE's code list an assignment of this sort, where we have the exponential function. Well, if we do a Taylor solver, it needs to compute the Taylor coefficients of V given the Taylor coefficients of U up to some order. Okay. And how to do that? Well, the way we're doing it now, this thing obeys this simple ODE. Okay. And we can write V dot equals V y dot when U and V are both functions of t. And the whole idea in the code list of the ODE, where something like this appears, to replace it by its sub-ODE. Okay? And as I'll explain later, by doing that, the whole thing becomes like using only basic arithmetic operations. So this is the idea of this sub-ODEs. But then it gets little involved. So if we take this simple ODE, its code list is given here using the definition. So given x, we can evaluate u, we can do this, and then we get x dot, which is the output. But now, if we replace this assignment here by this sub-ODE, then we end up, so we have a code list that represents not an ODE, but it represents a differential algebraic equation, or DAE. And the reason is that if we want to cast or express this as an ODE system, we must differentiate the second equation. There is no other way around. So using sub-ODEs, make an ODE into a DAE, and this required quite a few theoretical results that I will summarize some of them later. Okay. So this is one of the main things we get at the DAE. Okay. How to get the coefficients of this thing, if we have it? Well, similarly, we write formally the Taylor series for x, y, and x hat, and inserting in these equations, we have these relations. So this is x dot, which is x differentiated, x hat differentiated. U equals minus x, this is trivial. And then we have this x hat dot equals x hat times u dot. Okay? And again, doing this term by term, when k equals 0, we have an initial value. U naught is simply minus x naught from this thing here. And x naught hat, it doesn't appear here, but this is e to the power of y naught. So this is what we call built-in initial value. Okay? Once we get this, stage k equals 1, or computing the first coefficients, it's not difficult to see x1 is this one, y1 is minus x1. And then from this formula, x1 hat is x naught hat times y1. And similarly, when k equals 2, we get the coefficients and so on. Okay. Now, this has some nice consequences. So if we look at these recurrences, at k equals 0, we need to set initial values. And this is, I mean, we have them anyhow. And we have to evaluate these initial values for the sub-ODEs. But after that, only basic arithmetic operations are used, meaning k equal 1, 2, and so on. There are no standard functions whatsoever. And this applies for any sub-ODE. Not obvious fact, we never ask for values before they are computed, and in this case, we say the recurrence is sound. Okay, so whether we have exponential or sine or cosine or other functions, they appear just at the beginning. After that, the formulas are the same. Okay. So a little bit of theory, the sub-ODE concept. So here, we assume that g of u is an n-vector function of scalar u, and I'll show you on the next slide an example. And u and v are variables in the code list of the ODE. And assume that we can express this derivative of v as h of u of v for some suitable function h, such that this holds. Then this implies that this equation here, or in short, we have this, which we call the sub-ODE. Okay. And the sub-ODE method replaces in ODE's code list each assignment of this sort by the code of its sub-ODE. And here are some examples of this stuff. So I discussed this one. If we take the power function, u to some constant c, we can write obviously v dot equals this, and now our h function becomes this one. Right? Well, if we take, if we decide to compute sine or cosine, then our g function essentially is of scalar u and having two components, cos u and sine u. So v equals this thing. And when we differentiate it, it becomes this thing. So we have to specify this. Okay. And this is what we do in our implementation of this sub-ODE stuff. We specify the function, let's say the power function, to compute at k equals 0. And then we specify this function to compute at the other coefficients. Okay. And we have this operator, which we call it sub-O gamma operator. As an operator on functions, this means that this satisfies this ODE plus this initial value. And gamma is a base function, for example, like this one in the computer's numerical library. Now, as an operator on Taylor series, assuming this have Taylor series, one can derive a recurrence for this, which is not difficult to get. So what follows from this? Using sub-ODEs in the code list, we have only basic arithmetic operations and this thing. Okay. And what follows that when we implement this, the computational kernel, it has 5 operations. So the recurrences for this, again, this is not difficult to get. This is the function at the initial y naught, and after that, it is the same formula of any function. And we have recurrences for the basic arithmetic operations, meaning if we have Taylor coefficients of u and v up to some order k, plus and minus are easy, multiplication is just convolution, and division is a little bit more complicated than multiplication, but because we have to use the previous values of the result. So having 5 operations in the whole implementation has its own advantages, which I will discuss briefly at the end. Now, from a sub-ODEs from a DAE viewpoint, so I'll summarize some of the results. And one of the important questions is, if we do any number of sub-ODEs in the code list, are the recurrences sound, meaning can we compute that things don't break down? And to answer this, we use theory of amenable DAEs. So I'll slowly go through this. So if we take a general DAE in independent variables, xj, we have this system of equations. So derivatives can appear of any order. And okay. Now this is structurally amenable or amenable if from the sparsity pattern we can figure out how to solve it numerically. And in our case, it's verifiable by a certain Jacobian matrix being non-singular, which is also equivalent to the Pantelidis algorithm succeeding. And Pantelidis is something that it's been in industry for several years. And amenable is a common property in practice and assumed, for example, by Modelica, which uses Pantelidis. Okay. And what we know for sure is that amenable DAE has a solution scheme and an always sound recurrence for Taylor series expansion. So if we know that it has this property, we can always do Taylor series. So some key results, they're quite involved. So the initial ODE can be viewed as a kind of trivial DAE if written in this form. This always has amenable. Now this theorem, I'll explain the parts. If we take an expression psi in f, and if we replace it by a new variable and add a new equation, then the DAE is still amenable. So this is very much like sub-expression elimination. We pick up expressions, replace them by a variable, and we add an equation. And well, obviously, various systems do this. What wasn't obvious is that proving this turned out to be quite non-trivial. We struggled for weeks, as simple as it looks. So differentiating any of F's equations preserves S amenability. And if we replace, after we differentiate V equals GU, after we differentiate it once, and we replace it by sub-ODE, then it's still S amenable. So in other words, starting with an ODE and inserting any number of sub-ODEs, the result is an equivalent as amenable DAE. Okay. Well, what this solution scheme does is identical what the code list does. So essentially, we solve the original ODE as required. Again, the whole point is we start with an ODE, and all these transformations we do, we end up with something that is as amenable. So this is the theory part. So we have this implemented in a solver called ODTS, meaning ODE by Taylor series. And we specify the ODE the way it's specified in MATLAB's ODE suite. Now we generate code list by executing the function with using operator overloading. And once the code list is executed, then we evaluate it on each integration step to compute the coefficients. Now, if we have to do repeated integration with various initial conditions, we don't have to regenerate the code list. It's done only once. Okay? So I'll present some results performing the performance against MATLAB's built-in ODE solvers. So the first problem is a 2D mechanical system, 2 second-order ODEs reduced to 4 first-order equations. The second is Pleiades from the test set for initial value problem solvers. Describe motion of 7 stars, and it's size 28 when reduced to first order. And the Bruselator system, it models diffusion in a chemical reaction, and we chose it because this becomes increasingly stiff as sparse as we increase the problem size. Now, I'm going to plot work precision diagrams, which means CPU time versus significant correct digits, which are defined as minus log 10 of the relative error at the end. And we have accurate solution, and we compare against the accurate solution. So this is a standard way to assess solvers, and I've done this on MacBook Air. So for these problems, they are not stiff. Compare against these 3 solvers. And for the Bruselator, for sizes 2 and 100, these are the problem sizes, we compare with ODE 15S. Okay? So this is CPU time. This is significant correct digits in the plots. The red line means the time for computing, for generating the code list. It does look expensive. It goes through operator overloading, and there's lots of overhead when MATLAB executes this. So partly it comes from there. These plots here, so for example, this is ODE 113, ODE 45, ODE 89, and in red is the time for our solver. So it doesn't do bad here at all, but it's a relatively small problem. Okay. Here on Pleiades, we don't beat the MATLAB standard solvers, but I think I think it's possible to bring this, at least this line down. Okay. Bruselator, this is size 20. this is code list generation, but once the code list generation is done, we actually outperform ODE 15S for certain tolerances. We don't do here. Now, you may notice that here these lines have slopes, but here they're kind of horizontal, the computing times for the integration. And the reason this problem has stiffness and the step size is restricted mostly by stability. And when this happens, we take more or less the same number of steps for various tolerances. Okay. So some of the story. So automatic solution of initial value problems for this goes back at least to Raymond Moore in 66. He's given recurrences and lots of stuff in his interval analysis book. He also has a way of converting to an equivalent rational ODE, and he gives an example where these functions occur and they're eliminated. To our knowledge, Rick Neidinger is the first person to give an embedding method that can in principle be automated. And he has this operator kind of close to what we have, and he calls it DDOT. But they focus on recurrences without considering the differential system that is underlying them. Cordes and Ilya note that one can convert a DA to an equivalent one using only basic arithmetic operations, but they look at the system, not at the recurrences. So I'm close to the conclusion, and I'll show you something after the conclusion. So we have a theoretically founded method. The computational kernel consists of 5 operations. And what's nice about this is if we want to optimize for performance, well, optimize these 5 operations. That's it. I mean, plus and minus, there's nothing to optimize. There is just multiplication, division, and this sub-ODE. So we have a Taylor library of various functions, and they're very short. The code for programming this is very short. So with 135 lines of MATLAB code, we do this Taylor library. Now there's another thing that I have experimented with. Because we have only 5 operations, if we want to compute, let's say, derivatives with respect to initial conditions, we have to differentiate this, and we can do the forward mode. But if we do this, we do the forward mode only on 5 operations. So it's one thing to program this for 5 operations. It's a different to program for every separate function separately. So these 2 items feasible, and we've been working here on a user guide and tons of programming. So we aim to get this out. So this is my conclusion. I see I'm at 34 minutes, but I can give you an example of code list so you get an idea of what's happening. So it's a relatively simple system. So we have massless spring, natural length A, spring constant, and nonlinear potential energy. So I'm not going to go through the derivation of this, but they look like this, the equations. There are 4 equations. What I want to show you with the code list so you get an idea of what we execute. And it looks like this. So the first 4 lines, they are OD lines. These algebraic lines, meaning algebraic operation, meaning subtraction, multiplication. And these are sub-ODE lines, meaning this is going to be sub-ODE. And this is going to be sub-ODE. So here we have a cos, we have a sine, and they get computed here. And we have the exponential. So what this means, okay, so this is the kind. This means the operation. This means a mode, meaning whether the operands come from a register, so to speak, or immediate. So R is like a reference. All right? And for example, if I look at the sub operation, means a reference minus immediate. A reference is 1, means get this for line x1, subtract 1 immediate. Okay? This means multiplication, means multiply the results from line 1 and 4, which is here, x1 times x4. Okay? This also means multiplication. And this means computing x8 and x9. This is the input x3 to the sine and cosine, and x3 is the theta variable from here. Okay? Yeah, and 2 means I'm going to get the result from line 2, which is here. x2 dot 18 means I'm going to get the result from line 18. Okay? So this is the code list. Relatively simple. We generate this through operator overloading, and essentially this code list is an array of numbers, and we have a one-dimensional array of immediates. And when we evaluate it, when it comes to here, we call the multiplication operator. When it comes to here, we call the function for this sub-O operator. Okay? So this is 23 lines, and this is how they look like. Okay. Okay. I will say something that is not in this talk. Maybe it should be another one. We get Taylor series solutions, and we have additionally a system for doing operations with Taylor series. And one of the consequences is that we can very easily get Lie derivatives, but this will be part of another probably presentation another time. So yeah, I'll finish here and I'll welcome questions.
So many thanks, Ned, for your very, very interesting presentation, and definitely there will be some questions. Who wants to start with the first one?
Yes. So thank you, Ned, for the presentation. So I'm not sure I have understood first. Of course, you have a guaranteed result because you use intervals somewhere. Yes.
Well, the thing is, we don't use intervals. At the moment, it works with double and variable precision. I tried intlab. It's not difficult to run this through intlab, meaning through intervals. So it's not made at the moment to compute guaranteed solutions, but it is feasible.
Okay.
It's just changing the data type from double to interval. And I
Okay.
think this could be quite valuable.
Okay. So at the end, uh, you have an integration which is based on it's a Newton. No, not how you
Oh,
call
it's
it.
a Taylor series method.
Yes, at the end, so you obtain, uh, you are able to solve numerically
Yeah.
an ODE
Yeah.
using a Taylor method.
Mhm.
But I would like how I want to know if you have an automatic way to generate your coefficient, or if at the end you obtain a resolution method which is more efficient.
Well, we get this in an automatic way.
Yeah.
If we do this in pure double precision, we may, in some cases, we are more efficient than MATLAB solvers. In many cases, we are not. But this will have its advantages when, let's say, we run in variable precision arithmetic, because you cannot do, let's say, MATLAB's Runge-Kutta or multi-step in variable precision. And it will take advantages if we run, let's say, with intervals.
Oh, okay. And at the end, I would like to know what did you automatize in your library? For instance, you enter uh, uh, a string containing your state equation to be solved, and then after you have a parser which is able to build the abstract tree.
Yeah, well, it's kind of a representation of abstract tree.
Yes.
It's this code list, essentially.
Okay. Okay. I have understood. Thank you very much.
Yeah, maybe I shouldn't. I
Thank
just
you.
put the. So
Yeah.
yeah, essentially,
Ah,
let me see what went where. Yeah, essentially, we built something like this, which is printed in readable form.
yeah.
Yeah. So this part is codeless.
But it generates automatically
Oh, it's
from.
automatic. There's no manual work.
Okay. So you have to parse an expression containing your ODE.
Yeah.
Okay.
So it's let me see. No, we write at mm, mm, let me see. What do you- mm, so yeah, should have okay. Maybe mm, 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 mm. No, we give the ODE the way you give it to MATLAB. There's nothing different.
Okay.
And when this thing gets executed,
Uh,
then everything happens behind the scenes.
yes, because you are overloaded some the multiplication operator or.
Oh yeah, yeah, yeah,
Okay. Okay.
yeah,
Okay. I have understood.
yeah,
Perfect. Thank you.
yeah, yeah. Everything. So this are overloaded. So every time
Yeah.
we have an operation, it puts a line
Yes.
in the
So
code list.
so you don't need any parser.
No,
You
no.
mainly it's based on overloading
Mm,
your the structure you have behind
yeah,
what you call a code list. Yes.
yeah, yeah,
Yeah,
yeah,
I have understood. Thank you.
yeah, yeah. It's yeah. No parser gets executed on the fly.
Yeah. That's-
Yeah.
Yeah, the next question I think is something also related a little bit to the interior of your algorithms. Because what you did a couple of years ago together with John was publishing the DAETS solver.
Yeah.
And the structural analysis that you have in there, especially also for finding consistent initial conditions, is it exactly the same thing that you have included here, or has there been anything additionally added?
We don't have to find consistent initial conditions here. We just have ODEs.
Yes, can I come in and say, at the moment we've done the easy bit. We're solving ODEs, so there's no structural analysis needed. So the only theory is showing that this DAE, which gets created by the sub-ODE process, works. But as far as the solving the ODE is concerned, no analysis is needed.
Okay, then I would really like to test something as soon as you have published the code or your solver. Because what I did a couple of years ago, and I think John and you know this, I tried to use the DAETS in order to compute strategies for dynamic feed-forward control, where I have embedded some algebraic time-dependent functions as desired trajectories for some of the initial, for some of the state variables. And I think those expressions, they could easily be represented if you have well-behaved desired behavior. You could easily add them as the corresponding sub-ODEs that you have just presented in this presentation. And my feeling then is, since, as John just said, there's no further need for the structural analysis, I think the new version that you presented here, relying directly on the sub-ODEs, will be much more computationally efficient than the one that I tried out using the DATS a couple of years ago.
Yeah,
Very interesting.
DATS is based on FATBAT++, which is remarkably flexible and clever package, but it also has lots of memory operations and it has overhead. So getting this into actual C++ code can make things, I think, much faster.
Yeah. The other question that I had in mind, and I think maybe you have in mind something similar, since you mentioned at the very end of the talk that also Lie derivatives could be computed quite easily. And especially, we had this, I think it was around 3 years ago, here in the seminar series, a talk by Bernd Tipken from the University in Wuppertal. And he showed Lie series in order to prove the observability of nonlinear dynamic systems. And I think also this task of proving observability could also be a nice thing to discuss in some follow-up works, because it in fact just needs Lie derivatives to be manipulated in an intelligent manner.
Yeah, we can easily compute actually very easily Lie derivatives. One of the problems I have is I don't know them very well, and especially it's really important to get some good meaningful applications. So if you can suggest eventually some, it will be very, very good.
Yeah, I can send you a nice benchmark example because I think linear systems, they are a little bit boring. I think Luc knows this perfectly. In order to prove observability for a linear dynamic system, you just need to compute the observability matrix. You always know how many lines you have to compute, and that means, you definitely know also the number of Lie derivatives that are required. And for nonlinear dynamic systems, unfortunately, there doesn't exist such an upper bound. And I have in mind one article where proving observability is really tricky for nonlinear systems, and it's even especially
Yeah. Let me just show you very quickly. So this is the brusolite I was talking about. And the function is picked up from the MATLAB's demo, except that it had one vectorized part that we had to unvectorize it because we cannot handle it very well. But if I run this, so I give this make code. So we have a function make code list that takes the function, how many initial conditions, the size of the problem essentially, and it creates the code list. And if I run it like here, so the code list is 380 lines. And John implemented some sub-expression elimination that is pretty cool, right, John?
Yes, seems to work well.
Yeah.
Very
And
simple.
Once we have the code list, then essentially we pass the code list to the solver. And the solver just evaluates the code list. That's it. Yeah. Get a solution. Yeah. And we can pass the function. And if we pass the function, the solver generates the code list inside. The thing is that so this will compute the solution, but we also can compute. Need to. Doesn't like this. Okay, doesn't like when I break it. So in other what it can return. Just run it again. It can return the Taylor expansion of the solution at each point. And once we have this Taylor expansion at each point, and we have a function in this Lie derivative business, we can evaluate with these Taylor objects, and we get the expansion of the function, whatever g it is, so we can get all these high order Lie derivatives. So this can be quite useful. We just need to get some good application.
Yeah, and I think that's a really nice feature that you can make use of the pre-computed code list and then just re-evaluate it afterwards. And that's definitely a very nice means in order to reduce also the effort.
And we also can put parameters, so we can parameterize, and changing the parameters doesn't require evaluating the code list. It's just updating parameters in it. It's quite intricate, but works overall pretty good.
Ned, would you like to show page 5 and 6 of the user guide?
Oh yeah, that's a good idea. Just go there. User guide. Oh, here's a guide for 5 and 6. That's a good idea. Would you like to comment on this, John? No, this is. No, you're muted. You're muted, John. You're muted.
Oh, sorry, go back 2 pages.
Go back. Yeah. Here.
One, yeah.
Yeah. would you like to comment on? Oh, I comment.
Yeah, yeah. Go to the next page. Let's show how we actually do it. No. The page which had that bit of MATLAB there. No.
Oh, the here.
No.
Oh,
One back one page. There. Yeah. Okay. It says
okay.
G brackets YAD, right? That's how the actual calculation is done. So you have solved the ODE, and apart from the T and Y which MATLAB return, you can optionally return this AD tail object YAD, which holds the Taylor coefficients. G is just a function in terms of supported standard functions and so on, and you just evaluate it, and there you get the linear derivatives.
So the solver returns an object that contains Taylor series at each point, and then we just do this, and you get the linear derivatives.
That's fantastic. You'll get an example from my side.
Well, this is what we need.
Yep, please.
Okay, then let's have a look at the list of participants. Is there anyone else with a question? If not, let's thank Ned again for the excellent presentation, also for a little bit of live demo at the end of your talk. And yeah, I'm pretty much looking forward to getting access to the code to play around a little bit with control engineering applications with his help. And yeah, for now, I think the only thing I can do is I can thank everyone for attending today's seminar. Yeah, we're looking forward to the next talk, which we'll have on the 7th of March, where Hector Rios from Mexico will be the next speaker. And yeah, until then, I wish you a nice weekend and see all of you again soon.
Thank you, Andreas, for inviting.
Thank you.
Okay.
Bye.